so this is the last module for part 8. So for this module, we will be discussing the concepts and instrumentation of molecular mass spectroscopy. Okay, now this discussion is also applicable for atomic mass spectroscopy. Okay, so siguro when we reach a particular slide, no, isisingit ko lang din how that particular concept or part of the instrument is similar or different when it comes to atomic mass spectroscopy. So mass spectrometry is a very powerful analytical instrument, no? Mass spectroscopy, the technique, because this provides us with the elemental composition of samples, no, of your sample. So meron dalawang klase, no? You have your atomic mass spectrometry. It is actually used for determining yung different elements, no, present in a sample. Normally, for atomic mass spectrometry, it is used in tandem with your other techniques, no, such as your ICP, no, inductively coupled plasma mass spectrometry. So in this tandem instrumentation, where, well, in a way, your mass spectrometer serves as a detector, you would be able to have a very sensitive way of detecting the elements present in your sample, which was atomized by your plasma. For molecular mass spectrometry, the mass spectrometry is actually used for the elucidation of the molecular structure of your sample. So basically, in mass spectrometry, what we do is we break apart the molecule, okay, using this particular part of the instrument, yung ionization source. So we fragment, no? We fragment the molecule, and then we detect each of the fragments based on their mass to charge ratio. Okay, so from this fragmented sample, no, yung signals from the fragmented molecule, we try to elucidate the original structure by looking at this fragmented molecule as a puzzle, no, parang puzzle. So we try to elucidate, no, deduce the original structure, no, by looking at the possible structures of the resulting fragments, no, of the molecular sample. Alright, so again, this has been used for determining structures of inorganic, organic, and even biomolecules, no? So we can even use NMR mass spec, alright, for, say, determining the structure of proteins, no, or enzymes, no? So yung mga naririnig yung medyo bago-bagong fields, no, like proteomics, yung omics in general, no? Usually they rely on mass spectrometry, no, as one of their tools, okay, for elucidating the structure of these large biomolecules. Okay, so mass spectrometry can be used for both qualitative and quantitative composition, no? Determining qualitative and quantitative composition of mixtures, complex mixtures, and even to elucidate the structure and composition of solid surfaces, no? So if you've heard of your Mars rover, no, the Mars rover, yung parang robot na sinendun sa Mars, no, to study the Martian environment, this Mars rover is actually equipped with a mass spectrometer. Alright, so that in situ, in the Martian environment, rock samples or soil samples, so the chemical composition, the structural information can be obtained, no, on the spot. Alright, and one particular ability of your mass spectrometer is that it is able to determine yung isotopic ratios of atoms in the sample. No? So not only the presence, no, of each element can be determined, but also the amount of each isotope in your sample, no, for each element in the sample. Okay, so this diagram shows you the basic instrumentation of a mass spectrometer. So you have a sample in the system. Now, since your mass spec is a very sensitive instrument, meaning to say it's able to detect even the tiniest concentrations, no, of your sample, it is important that we reduce, no, the amount of the sample that is introduced into the mass spec system is very, very small. Okay, so in case of tandem instrumentations, no, yung kinokopol natin yung mass spec, such as ICP-MS, LC-MS, or GC-MS, the integration, no, of the sample inlet system allows for the delivery of a minute portion of the sample, no, coming from the plasma or coming from the LC or GC systems. Okay? For standalone mass spectrometers, no, so marami ring klase ng sample inlet system, but all are designed to allow a very, very small fraction of the sample to be introduced into the system. Okay? So basically, yung mass spec has four major parts. You have the ionization source, you have the ion accelerator, you have your mass analyzer, which is the heart of the mass spec. Okay, so dito nangyayari yung separation of your fragments in terms of their mass to charge ratio. Okay, the mass analyzer is actually analogous to your monochromator. So if you remember sa monochromator, anong ginagawa, no? So grating monochromator yan. So for the grating monochromator, the angle, okay, the angle of the grating is gradually changed, no? So merong mechanical part sa monochromator that allows for the slow changing, no? Slow and accurate changing of the angle of the grating. So depending on the angle of the grating, yung wavelength of radiation that will come out of the exit slit and hence be detected by the detector. Okay? So dahan-dahan ginagalaw yung angle nung grating so that the detector would be able to measure the intensity or the power of radiation from each of the wavelengths. All right? That is being dispersed by your grating. So similarly, in mass spectrometry, by varying some parameter in the mass analyzer, we are able to allow only certain, or sorry, not certain, but we are able to allow fragments with a certain number or certain value of mass to charge ratio to be detected or to pass through the detector. Okay? So sa ganung paraan, we are able to measure the relative intensity, no, or yung relative na dami, okay, ng bawat fragments associated with a certain value of the mass to charge ratio. Alright? Now, this whole system is under vacuum, no? And ito yung isa sa nagpapatagal ng isang mass spec analysis because you need to ensure that the required level of vacuum inside the system is achieved. Okay? Bakit? No? Because the presence of atmospheric gases or even dust can actually wear the instrument down and really interfere with your analysis, no? Because what we have here, if you have molecular mass spectrometry, you have what they call this, molecular ions, no? So these are charged molecular fragments. So if you have atmospheric gases or even unwanted molecules inside the system, this would actually deactivate the fragments, no? Making them lose their charge, no? And hence, mawawala na yung kanilang response, no? Towards the detector. Alright, so very important that the instrument is under vacuum. So here are some of the sample input systems used for mass spectrometry. So you can just read this through. But what's important is that for all of this, again, the objective is to introduce a very, very small fraction of the sample into the instrument. Again, why? Because the instrument is very sensitive. Okay, so you don't want to overload your mass spectrometer. So next, you have your ionization sources. So for molecular mass spectrometry, this is the part of the instrument that converts, fragments, no, your molecule into different fragments, no, molecular ions. Alright, so there are many types of ionization sources. Okay, may advantages and disadvantages ng bawat isa. And some ionization sources are chosen depending on the type of analyte being analyzed. So some of the examples of ionization sources. So first you have your electron ionization, and this is one of the most commonly used ionization sources in organic mass spectrometry. So here, electrons are being emitted from these filaments, no, usually made from tungsten, and these electrons, no, emitted at high acceleration, is used to heat your molecules, no, your analyte. And by heating the molecule with these electrons, we are able to ionize, no, so we knock off, okay, an electron from your molecule, and this causes a subsequent fragmentation of the sample. Now, from organic chemistry, I hope you recall that molecular fragmentation in mass spectrometry actually occurs in predictable mechanisms, no? Yung mga tinatawag nilang mga Glycine fragmentation, or yung mga alpha cleavage na tinatawag, or if you have an OH, no, you have yung dehydration. Alright, so yung mga ganong klaseng fragmentation mechanisms, no, resulting into well-known fragmentation patterns. Okay, so that particular mechanism is induced, no, by your ionization source. Now, because the electron, alright, emitted by the electron gun, alright, or yung isang tawag dito, no, sa filament na ito, is highly accelerated, highly energetic, this method is usually called hard ionization. Okay, and this usually generates a mass spectra, that has many fragments, no, and that reflects the strength of ionization, no, induced by electron ionization method. Alright, so next you have your chemical ionization. So chemical ionization, in contrast to electron ionization, is a soft ionization method. So pag sabing soft ionization method, it does not lead to extensive fragmentation of your molecule. So how do we do chemical ionization, no? So basically here we use a reagent gas. Alright, so there is a huge excess, no, a large excess of a reagent gas, usually present at around 1,000 to 10,000 times higher, no, concentration than the sample. Examples of this reagent gas are your methane, isobutane, and ammonia. So what we do is we also have that electron beam, no, weaker electron beam, which initially ionizes your reagent gas. Okay, now this ionized reagent gas then interacts with your analyte, no, your molecular analyte, wherein they steal an electron from your molecular analyte, no. So again, this ionization induces now fragmentation, no. So similar dun sa kanina. Yan, no. So sasabi natin kanina. So the reagent gas is ionized and allowed to interact with your analyte molecule, and this induces ionization and then subsequent fragmentation. So again, the spectra coming from chemical ionization, okay, contains lesser number of peaks, no, compared to your electron ionization. Next, we have your electrospray ionization, or ESI. So this is a type of atmospheric pressure ionization wherein the ionization process is induced under atmospheric pressure, no? So yung kanina, electron ionization sa chemical ionization, both nung system nun ay inside the vacuum of the mass spectrometer, no? But for electrospray ionization, it is actually under atmospheric pressure initially. And this is actually used for LCMS, no? So remember, for liquid chromatography mass spectrometry, yung ating analyte is actually dissolved in the mobile phase. Alright? So nasa ano siya, no, solution phase. Alright? So we need to have a method of first dissolvating the analyte, no? Dissolvating the analyte, okay, and then introducing a very small amount of the analyte into the mass spec system. Alright, so electrospray ionization allows for that. Alright, so basically what it does is that you have the sample comes out of this metallic capillary. Okay, so a strong electric field is applied to the liquid passing through this metal capillary, which in effect disperses the liquid into a fine spray of positively and negatively charged droplets. Alright, and this is your electrospray, no, hence the name. And this technique is useful for large molecules, no, such as proteins, also for elucidating protein structures using LCMS. Next, we have your matrix-assisted laser desorption ionization, or abbreviated as MALDI. Okay? So here, with MALDI, flash natin na siguro. No? Alright. Ayan. So basically here, we mix your analyte molecule. Okay? Your analyte molecule, no, which is usually large analyte molecules, no, with a smaller matrix molecule. Okay, so an example of this matrix molecule could be your hydroxypicolinic acid. Alright, so here what we do, so you mix the your molecule into your matrix, and then using a laser beam, no, the laser beam induces simultaneous ablation and ionization of the material, no, which is adhered on a solid matrix, no, or solid substrate. Alright, now selective ionization is possible by choosing the appropriate laser wavelength, no? So pwedeng sadyain na ang mag-ionize lang ay yung analyte molecule imbes na yung matrix molecule. Okay, yan. This technique, MALDI, is used for macromolecules, no, for the analysis of macromolecules, no, such as again proteins. Okay, and this method is a soft ionization method. So your mass analyzers, this is the heart of the mass spectrometer. So the mass analyzer functions like your monochromator. Okay, wherein each fragment with a corresponding mass to charge ratio value is being some sort of parang filtering, no? Is being filtered one by one per m to z value, so that each of the fragments will go to the detector, or be detected by the detector. So the first one, there are many kinds of mass analyzers, but for this module, we will be just discussing 3 of them. So the first one, you have your magnetic sector. After the fragments comes out of the ionization source, it will have the same kinetic energy. But when it goes through the magnetic sector, okay, the different values of their corresponding m to z mass to charge ratio will make the ions emerge from the magnetic field at different position. So this the value for the magnetic field in the magnetic sector is being varied gradually, so as to allow only the desired value of mass to charge ratio to exit through this exit slit and go through the detector. Alright? Yan. So, binavary ito. So, this is again analogous to the movement of the grating in your monochromator. So, here, instead of a grating moving, you have the magnetic field value being changed gradually. Okay, so next you have your quadrupole mass analyzer. So, as the name implies, no, it has 4 poles, alright? And in the middle, in the gap of these 4 poles, is the ion path, no? So, this is where the fragmented ions will pass through. Okay? Now, the quadrupole separates ions in an electric field that is varied with time. Okay, so similar to your magnetic sector, no? Sa magnetic sector, magnetic field yung vinavary. For quadrupole, it's the electric field or the quadrupole field that is being varied. Alright, so the field is created using an oscillating radio frequency voltage and a constant direct current. Alright, so by changing this quadrupole, the value for the quadrupole field, only one value of mass charge ratio is allowed to pass through at a given time. So again, similar doon sa ating monochromator, you are scanning, no? You are scanning the for each m to z value that you will be allowing to pass through the detector. Okay? So the other fragment, alright, nakaset ito sa mass to charge ratio value 50, for example, no? So those that are lower or higher than 50 will just hit the poles. And since the poles are electrically charged, it will neutralize the ions, okay? So preventing them from reaching the detector. Okay, so lastly, you have your time of flight mass analyzer. So the time of flight mass analyzer is, well, this is just a 1 to 3 meter evacuated tube. Alright? So it's field free, meaning to say, unlike magnetic sector and quadrupole, there are no electrical or nor magnetic field. Okay, so for the TOF, they like to call this the TOF, no? It does not use external force to separate ions of different mass to charge ratios. So the pulses of ions, okay, are accelerated from the ionization chamber, no? It is accelerated into this drift tube, no? The length is again, no, around 1 to 3 meters, no, depending on the unit. All right. Now, so we said earlier that ions, after coming out of your ionization chamber and ion accelerating sector, the ions would have the same kinetic energy. However, the corresponding velocities of these ions will depend on the mass to charge ratio. And since in mass spectrometry, mostly your ions have a just same charge, no, what will happen is that the ions will travel this drift tube according to their corresponding masses. So in general, lighter ions will travel faster compared to heavier ions. So again, ang keyword dito is that there is no external force, no, used to separate your ions. No, they are separated based on their velocities. Again, the trend, lighter ions will travel faster than the heavier ions. Alright, so for the detectors, for your mass spectrometers, they are basically ion detectors. No, so the first one, you have your electron multipliers. Alright, they function, no, just like your photomultiplier tubes. No, so basically these are for positive ions. Okay, the surfaces of the cathode and the diodes are doped. Okay, for discrete diode, it's made from copper, beryllium dope. No, whereas for continuous diode, it's a glass which is heavily doped with lead. Now, in general, electron multipliers are rugged and reliable, and it has very fast response time and high current gains. So, meron ka ng internal, similar to PMT, no? Meron ka internal amplification dito sa electron multipliers. So, lastly, we have your Faraday cup collector. Okay, so similar to your electron multiplier, this is also an ion detector, no? So this particular transducer is aligned along the path where ions existing, the mass analyzer, and the ions will be striking the collector electrode. Now the Faraday cage prevents the escape of the reflected ions and ejected secondary electrons. Now the advantage of Faraday cup collector is that the response, okay, is independent of the energy mass nor the chemical nature of the ion. So it does not discriminate, no? And it is also inexpensive and simple both in its electrical and mechanical makeup. However, a disadvantage of Faraday cup collector is that it needs high impedance amplifier, which limits the speed at which a spectrum can be scanned, and it is also less sensitive compared to your electron multipliers. Okay, so that's it for Module 7. Again, I'll just be posting the self-assessment exams in our FB group page.